So we'll be starting. So again, welcome, Vincent. Extreme deduplication using the Scala ecosystem. The stage is yours.
Yeah, thank you. Thank you very much. All right, people, welcome. Good afternoon. I'm going to talk to you about extreme deduplication in the Scala ecosystem. I think deduplication is something we all try to do in our code. We try not to duplicate code, not to repeat ourselves. And in most cases, this goes pretty well because within an application, I see a lot of people not duplicating code. But when you zoom out a bit and you look at multiple microservices, or you look at the infrastructure code or other parts of the ecosystem, then I see a lot of duplication actually. And today we're going to try to get rid of that. So I'm going to try to squeeze all the redundancy out of the code that we have. But first, let's tell you a bit about myself. I'm Vincent de Haan. You can see my GitHub link on the sheet as well for if you want to see the code that I will be talking about. And I'm a Scala developer. I live in Amsterdam. I work as a freelancer. I think I have been working with Scala for 5 or 6 years now. And in my free time, I like to run, to ride my bicycle, and to read a lot. And I was reading this book some time ago. Maybe you have heard of it. It's a Pragmatic Programmer. It's almost 25 years old. It's from 1999, but it still contains a lot of wisdom, I think. And let's see what it has to say on deduplication. And there's actually a section in it that's called the evils of deduplication, of duplication. I'm sorry. So that seems relevant. And they also give a rule or a definition of what they try to accomplish with duplication. And let's look at that very closely. Because they say every piece of knowledge must have a single, unambiguous, authoritative representation within a system. And this tells us also why we do not want to duplicate our code. It's not about typing less. It's not about saving bytes on our hard drive. It is about representing each concept in exactly one place. And the reason that we want that is because if we represent concepts in 2 places and we change the concepts here, and all our concepts change all the time because we have different requirements, or we fix bugs, or we get a better understanding. So the concepts and the knowledge about it changes permanently. And if we have the concept stored in 2 places, then if we change it in one place and we forget to change it in the other place, or we change it but we change it not in the same way, then we will get inconsistencies, and these inconsistencies are a frequent source of bugs. So this is what we are trying to prevent here, and that is the reason that we are trying to deduplicate our code. So it's not primarily about typing less, it is about representing each piece of knowledge in only one single place. All right, so what are we going to do today? We are going to build a simple HTTP application. That's not hard, I would say, but we are going to look around it and look at the whole ecosystem. And an HTTP application needs also documentation. For example, in OpenAPI. Maybe we have a front end connected to it. So we also need to look maybe at TypeScript models that can be used by front-end developers that want to connect to our HTTP server. And we need to connect to a database. So in this case, I chose DynamoDB from AWS, and we will also look at that. And we will try within this application and with this bigger ecosystem to give every piece of knowledge exactly one single place to be represented. All right, let's start with the documentation. Because if we have an HTTP server, we will have endpoints, and these endpoints need to be documented. And documentation is, in a sense, a form of duplication, because we have the code and we have the documentation, and they contain the same knowledge. So if we want to get rid of that form of duplication, we can, for example, generate the code from the documentation. Well, I've seen people try this and it works, but it's a bit messy because then you generate the code from the documentation, and then you have to merge in some way that generated code into the rest of your application. And then you change the documentation and you have to regenerate the code and then merge it again. So this in theory it works, but in practice it's a bit messy sometimes. Well, you can also try it the other way around. You can take your Scala code and generate the documentation from there. I've also seen this working, but it's even messier because the code can be infinitely complex. So if you want to create a tool that creates the documentation from it, you have to have a tool that is either infinitely complex or you have to use only a subset of the Scala code to write your endpoint. So either way, it's not ideal. So I think the best solution here is to try a third way, to create a general description of the endpoints that we want to represent that description in Scala, and from there generate both the documentation and the HTTP application. And this is exactly the approach that is taken by the library Tapir, which I will now show you. And I believe that's actually written mainly here in Poland, so that's a nice touch for today. What this library does, it allows us to represent all the knowledge that we have about our HTTP endpoints in Scala. So suppose we have this endpoint. It's a post endpoint to an address with the content type and some JSON data. Then we can represent it like this. So we can see here clearly that we have the post, we have the part of the URI that we have as input. We have the JSON body. I called the class name foo. We have a status code as endpoint, and also we have the human readable description. So this, of course, is not relevant if we want to run the endpoint, but if we want to have the documentation, then the human readable part is important. And then we can also add the server logic, and this is just a function of the right type. And I added a dependency here on a trait which implements this function. And now this is a description of the endpoint that we can use to generate both the documentation and the actual server. So let's see how this goes. So here we can we have a small application that generates the documentation. So we have Tapir gives us an open API docs interpreter, which interprets the data structure that we just built as documentation. Well, that happens here, and the rest is only the things we need to do to actually output the file, and now we can generate the documentation from the code. The same way we can also create the HTTP server, and we don't even need to generate the code because we are already writing code, but we can generate the HTTP server from the intermediate representation. So we get this akka HTTP server interpreter to interpret the endpoint as an akka HTTP server. We can also choose other commonly used HTTP servers, but I chose akka. And you see here that we have now to supply an implementation of the service trait where we can actually implement our business logic. So I think this solves the deduplication problem for HTTP documentation quite well. And now we have only one place where we have represented the knowledge about our endpoints. So let's look at the SPT project structure that we can use to implement this. So we have 3 sub-projects now. So I have one sub-project that contains the domain objects and the description of the API. And then I have 2 actual applications. One is a main function that generates the documents, and one is the actual service. as you can see that the knowledge is represented only at the level where it's necessary. We will expand on this diagram later when we are adding other parts to our application. Because the next challenge is the TypeScript model. So maybe we have a front-end developer also working on our team who creates a front-end for our application, and he works in TypeScript. And in TypeScript, we of course have types, and we have also interfaces for our domain objects. And they are the same as the case classes in our backend application. So if I give him the documentation and he has to write his interfaces, then in fact he is also duplicating code. So a better way would be to generate those interfaces from our domain objects. And for this reason, an SBT plugin exists that we can use. So first, we need to put all the domain objects in one folder, and then we can easily enable this plugin. And then we have to, the designer of the plugin says, well, you have to give me a list of all the classes for which you want to generate the TypeScript interfaces. So we can do it like this. But then again, we are duplicating because we have the list of classes already in our domain objects implemented, and then we have to give a list of them as well. So this is, again, a form of duplication. So let's try something different, and then I came up with this. And this is a little messy. So but this is the best I could come up with on a late Saturday nights. And I think it's not too bad, because you only have to set this up once. And when it works, you never have to touch it again. Well, your domain models, you may touch every day because you add new fields, you add new objects. And I think if you need to make a mess somewhere, then and it's better to make a mess in a place where you never have to touch it again than a place where you work every day. So I think it's a good trade-off to do it like this, but I think there are better ways to do this. So if you think this is a good approach, then I would challenge you to come up with something better. And then we have to add a few more configurations to make it work. And now we can, with a single command, we can generate all our TypeScript models, hand them over to the front-end developers, and we don't have that kind of duplication anymore. And now we see that we have this SPT project structure, and we see that the domain objects are on the top of the hierarchy, which means that the knowledge of the domain objects is necessary for everything that follows, and the knowledge of our endpoints is, for example, not necessary to generate the TypeScript model. So that's why we have put it in a sub-project that's lower in the hierarchy. All right, now let's go to the database requirements, and I think this is the most complicated part of the talk. And I'm going to warn you, I will also not explain everything that's happening here, because I will make use of the library Shapeless a lot. It's a library that's used for generic programming and type level programming, and we could talk about it for hours. It's a very interesting topic, but it's not what this talk is about. What the talk is about mainly, I think, is to convince you that these requirements are actually the requirements that you should be aiming for. And I'm going to implement these requirements. I'm going to use a lot of Shapeless magic to accomplish that. And I think it's very interesting, and it was a lot of fun implementing it. But the most important thing for today is that these requirements are actually the requirements you need to get rid of some duplication in your database code. So let's see what those requirements are. And let me first give you the motivation for it. I think we all know the situation that you deploy your application to the server, you run it, and then you get an error table does not exist. And what happens, either you forgot to run your infrastructure code, or your table has a different name than you configured in the code, or there's a mismatch between what's actually in the database and what you thought was in the database. Or you run a query and index does not exist. And then again, there's a mismatch between what is actually on the server and what is in the code. Well, these, if you think about it, these errors come from duplication, because their knowledge about what is represented in the database is in two places. And I think with these three requirements, we can solve that problem. So the first thing is, I can only create a repository of type T if a table for objects of type T actually exists. I can only create an index for a field F if F is a field of type T. And I can only create a query on an index if that index exists in the database. And I would like to check these requirements at compile time. So I would like to encode them in some way in the type system, maybe, that the compiler actually tells me that one of these requirements is not satisfied. And then that's very, very complicated, because the compiler cannot connect to the server and see what's actually there. So I'm going to change it a little and say that I want the compiler to check if my code in the application conforms to what is in the infrastructure code, because that is possible, I think. And if I can satisfy these requirements, then I can be sure that when I deploy my application to the server, everything will work fine. So let's start at the first requirement, and I think we should use the same idea as when we were implementing the OpenAPI documentation. So let's start with an intermediate representation in Scala, where we describe our database. And then this intermediate representation feeds both the CloudFormation template and the application. So for those who are not familiar with AWS, in AWS you can use CloudFormation, which is a YAML file which describes the resources, for example, tables that you need on AWS. And when you deploy the CloudFormation template, AWS makes sure that the resources that you have ordered will be there. And the idea is, if we can generate the CloudFormation template in Scala from this database representation, then we know exactly what is there. And then if we implement our build pipeline in such a way that the template is always deployed before the application, then we, in fact, also know what will be on the server when the application arrives there. So I think this might work. So let's describe our database. And the most simple description of a table is just that it is a table and the name. So we can define our tables like this. But we can enter everything we want here, because this is just a string. So this is not strong enough, because now we don't know that this table actually contains full objects. It just has this name, which is just a string. So we need to find something stronger, I think. So maybe let's try it with a type parameter, because then if we have a typed table, then we can be sure that we in some way connect the type of the things that we are going to store in the table to the description of the table. So this way we can describe the tables, and the more observant of you will notice that there is an H before nil, which means that this is a bit of the shapeless magic I was talking about. So this is a heterogeneous list. Not going to explain in detail what it is, but it is not a normal list. Let's keep it at that. And now we have a description of our tables, and we can be sure that these tables can only be described if these types actually exist, because I cannot describe a table for a type that does not exist. All right, and now I'm going to create a repository, and let's first start with an abstract class for all our repositories. And there I create this protected val table info of type T. So I have a repository of type T, and I need a table info of type T. And when I want to implement this thing, in some way I need to find a way to create a value for this thing, because otherwise I can't, the class needs to be abstract and I can't create this class. So then I have to go to my tables list that I defined earlier and select in some way the table of the right type. Well, because it's a heterogeneous list, it's a list with things of different types, I have to do a little magic to actually select the right thing. So that's what this object is for. But the thing is, it is impossible to create this value without referencing to the tables list that I had defined before. So now I know for sure that I can only create a repository of type T if I have the table defined in my intermediate representation. And if I then use that representation as well to generate the CloudFormation template, then I know for sure that I can only create a repository if there exists a table for type T in the infrastructure code. And that's exactly what the requirement was. So let's look at the second requirement now. I can only create an index for a field f if f is a field of type T. I've repeated the case class foo here. Of course, this is just for reference because it will be in the domain package that I showed earlier. And now I want to define in my table description, I want to define indices on the table that are fields of the type that we are storing in the table. So we could do it like this. But again, this is not strong enough because because the compiler cannot check that this string is one of these fields, because I can enter anything I want here and the compiler will agree. So I need to do some magic again. And that's where, again, I have to apply a bit of magic. This is, by the way, also how many JSON serialization libraries work. They use the same mechanisms. And what I do here is I make sure that I can only add an index if the field with the same name is actually defined on the type. So then we can represent the tables this way, and this is illegal because we have the name here and bar name here on the class bar. So this is what we want. And when we try this, and we add the wrong name, and we try to compile this, we actually get an error at compile time because the compiler says could not find implicit value for parameter selector, which means that it cannot prove that foo has a field with the name wrong name, and it hasn't, so it's correct that it cannot prove it. So this way we can be sure that we can only represent the things that we want to represent, and then when we later on use this information to feed our repository, that we can only query the indexes that actually exist. So then we get to the third requirement. I can only create a query on an index if that index exists in the database. Well, let's first look at how we would normally do this. So normally we would have a repository, an abstract class with a getByIndex function maybe, which calls the database client. We use Scala, which is a Scala library for DynamoDB. And we would ask the database client to give us the value where the index has a specified value. Well, And then in a specific repository, we would just say get by index with index name and with some value. But this does not guarantee us that this index actually exists. So this is not strong enough, I think. So let's see how we can solve that with our new database representation. Then we have to do a bit more work, because here with this in this get by index function we require an implicit typed table which gives us all the information about the table, including the indexes that we have defined. And here we supply this type table implicitly, and now, thanks to all this magic, the compiler can actually prove that the index with this name exists. And if it cannot prove that, then it will throw a compile error. So this way, we can be sure that when we deploy our application to the server, that all the resources that the code requires will actually be there, if we have correctly deployed the CloudFormation template, of course. Well, let's look at what the SPT project structure looks now. So here we see that the domain objects are still at the top of the hierarchy. The database definition depends on that, because you cannot define the database if you do not know what is stored in it. The HTTP service depends both on the database definition and the endpoints. We also have a CloudFormation generator. I didn't show you how this works, but if you're really interested, you can look it up in the GitHub repository. Well, this of course does not depend on the HTTP endpoints, because it's totally different part of the application. And now we can see that all knowledge is represented in exactly one place, and that it is in a logical place in the knowledge hierarchy. All right, so I think this is a nice example of how we can do it, but of course it is not the real world that we live in, because this application doesn't exist. It exists only on my machine. It works. It was fun to create it, but I don't believe that any of you will now next Monday start from scratch and write applications like this. Don't believe that, and I think that's also not possible. So let's go back to the real world, and I want to ask 5 questions to you to think about, because I think we can learn something from this idealized representation. And the first question is, do you have shared domain model between your services? Because we all have domain objects, and what I see a lot of times is that people in different microservices every time again define the same object for each microservice again, and then the services communicate. So apparently they're talking about the same objects, or at least about the same things, but they are defining new objects every time. So I think this is a part of deduplication that you can start with tomorrow, and you also don't have to make your whole business domain shared, but you can start just with a few objects. And ideally you would do it in a whole company. But even if you just do it with your team or with a few teams that are working well together, then it would already be an improvement. The second question is, do you generate documentation? Because documentation is by definition a form of duplication, because you have something in the code and then you're going to write about it. So that is, by definition, it's a form of duplication. And because it is, it's always hard to keep it in sync. Because you have written beautiful documentation and then you change the code and you forget to change the documentation, and then the documentation is not synchronized with the code anymore, and then the problems begin. And you don't have to generate all your documentation. I don't think that's possible. But if you generate at least some of it, that would help a lot, I think. Do you generate your infrastructure code? Well, personally, I don't like writing infrastructure code because it's always boring, it's repetitive. I don't not really interested in how queues work, how databases work. It's not my preference. So if I can generate it, then first I can do what I like. I can write code, and I can be sure that the infrastructure is in sync with the application, because I can create a common representation that I can use to feed both the application and the infrastructure generator. And again, you don't have to generate all your infrastructure code, but even if you just start by doing little bits and pieces, I think you can improve. And this is a practical one, and I think you can just look this up, because you must have had a situation where you had to add one field to a case class. I think I do it every month at least. And then you have to go to GitHub, look at the pull request where you did this, and see how many lines you had to change to add one field to a case class. And in most of the cases, it will maybe be 40 or 50 in some code bases, which means that there's a lot of duplication. And of course, you have to adjust some tests if you add a new field. But if you have to adjust all your tests, then probably you could be more efficient. And then the last question is, do you always solve the problems where they occur? And of course, we try this, but then becomes a bit more difficult, because the problem occurs in a software that's maintained by another team. So then you have to ask the other team, hey, can you prioritize this? It's difficult. Or maybe it's even worse. Maybe the software, the problem is in an open source library, and then you have to create a pull request, and you have to wait till the maintainer has reviewed your pull request, has created a new version, and it can take months. So then you need to make a workaround in your own code. But do you also create a PR on the external library and then wait till it gets reviewed and the new version is out, and then import a new version in your own code and remove the workaround? Because that's, I think, the way it should be done. Of course, we never do this all the time, but do you do it at least sometimes? I think if we think about these questions, we can gradually make our code cleaner and more efficient and make it easier to maintain. And these questions all concentrate on some aspects of deduplication and on concentrating the knowledge in a single place. So I think these are the questions we should be thinking about. And that's what I wanted to tell you today. Thank you. Any questions?
Which are the reasons for this idealized architecture for not being practical? Yes, you talk about this idealized architecture.
Yeah.
Okay, but you said that it's not practical. So which are the reasons?
Yeah, well,
being able to program in this functional DSL-based architecture.
Yeah, well, the main reason is that we all have existing code that we are using, and we have to, in some way, get it into this quite strict framework. That's hard. We also communicate with other systems, so maybe we don't. If we are going to generate our TypeScript models, then the front-end developers have to be on board as well. So I think it is possible if you start from scratch, if you have everyone on board. But in practice, things get out of hand.
For sociological reasons.
Yeah, exactly.
Technical.
Yeah.
Thank you.
All right, well, thank you for your attention.